We start this chapter on simple harmonic motion and elasticity with a discussion of the ideal spring and simple harmonic motion. Springs are familiar objects found in a range of applications, from push-button switches to automobile suspensions. A spring will respond to a push or a pull by compressing or stretching. For small displacements, the relationship between the displacement x and the magnitude of the push or pull force is linear. This linear relationship can be expressed as an equation by introducing a proportionality constant k, so that we can write Fx applied equals k times x. The constant k is called the spring constant and has dimensions of force per unit length, and the units are Newton meters. To compress or stretch a spring, a force must be applied to it. In accord with Newton's third law, the spring exerts an oppositely directed force of equal magnitude. This reaction force is applied by the spring to the agent that does the pushing or pulling, or to the object to which the spring is attached. The reaction force, Fx equals negative kx, is called the restoring force, and the restoring force of an ideal spring is stated in Hooke's law as follows. The restoring force of an ideal spring is Fx equals negative kx, where k is the spring constant and x is the displacement of the spring from its unstrained length. The minus sign indicates that the restoring force always points in a direction opposite to the displacement of the spring from its unstrained length. When the restoring force has the form Fx equals negative kx, the resulting motion, assuming no other forces such as friction are acting on the object, will be simple harmonic motion. Simple harmonic motion is an oscillatory motion that is common to many physical phenomena. It is easy to imagine a horizontal spring originally stretched some small distance from its unstrained length and released. The spring doesn't simply return to its unstrained position, but rather passes through it and compresses by the same amount it had been originally stretched. The restoring force will then cause it to again pass through its unstrained position, now going in the opposite direction, and stretch again. Without some force, such as friction, interfering, the process will repeat itself indefinitely. Suppose a pen is attached to the end of the spring and writes on scrolling paper as the spring oscillates. The result will be a graph of the position of the object as a function of time. The oscillatory function is a familiar one, a sinusoidal function, sine or cosine. Such behavior is a trademark of simple harmonic motion. Note that the position x reaches extreme values at positive a and negative a. A is called the amplitude of the motion. Now consider the case of a mass hanging from a vertical spring. Without the mass, the spring has some unstrained length. When the mass is suspended from the spring and is slowly lowered, it becomes stationary at a new position called the equilibrium position. At this point, the weight of the mass equals the restoring force of the spring, or mg equals k times d0. The new equilibrium position is therefore d0 equals mg divided by k. If the spring is now displaced from its new equilibrium position and released, it will undergo simple harmonic motion. In summary, Hooke's law states that, for small displacements, the restoring force of a spring is given by Fx equals negative kx. Whenever the restoring force is given in the form of Hooke's law, the result will be simple harmonic motion, and the displacement as a function of time will be sinusoidal.